Awesome. So thanks to the organizers for putting together such a wonderful workshop. I'm Harley. I'm based at the University of Chicago. And I was going to talk to you about both observations and simulations, but I lied. It's just going to be a simulations talk. So for those observers, which I think is most of you, feel free to fall asleep. No, actually, I'll briefly mention observations. So I want to start by highlighting the fact that, the high redshift ISM is weird. Dan highlighted this morning. I'll show you 3 examples of this. Some galaxies have very peculiar chemical abundances. This is, GNZ11 from some work we did with Alex Cameron, and you can see the nitrogen to oxygen is just well above what you expect from sort of lower redshift galaxies. Alice and Dan both talked about this. In some cases, the temperatures and densities of the interstellar medium are like stupidly high. 10 to the 5, that's like 3 orders of magnitude higher than we typically observe or typically sort of assume. Now there's a couple objects, including GNZ11. Some of the temperatures are being reported well above 30,000 Kelvin, in particular a paper by Isaac Lassiter. And we need to explain that. In some ways, this is kind of linked to bursty star formation or sort of super star cluster formation. So over the last year, have sort of tried to find observational examples of galaxies undergoing very, very extreme starbursts. I've put together a catalog of around 60 of them, but since version 3 of the DJA came out, the catalog is now about 150. We were looking for them via this Balmer jump, which is a feature of the nebular continuum, which you see comes up beautifully in the stack, and it's a very clear signature of a galaxy undergoing a very, very extreme starburst. What's interesting is among this catalog, there's sort of 3 galaxies that show very peculiar features of both a Balmer jump, something that looks like it could be a DLA, but then also extremely strong Lyman alpha emission. If this is a DLA, it's the highest DLA column density we've ever observed for a galaxy, and there's 3 of them that look identical, which is very peculiar, so you can interpret this differently. You can interpret this as something like very massive stars. Now, this is just to highlight that it's weird, but we need to explain all of this. Also, there's plenty of other people showing these weird features as well. It's not just us. And the typical way we explain these galaxies is by using photoionization models. So this is my best representation of a photoionization model. You have a stellar population in the center of a spherical or slab of gas. And these are great, right? I mean, these are super cheap to run. You can run millions of them. It's super parallelizable. They include, all of the physics you could potentially need to make these observables, various emission lines, et cetera. But I just want to highlight that a real galaxy looks like this, which is clearly different. And it's obvious that we're missing a lot of the galaxy formation physics, whether, adiabatic expansion, compression, shocks, feedback, turbulence, et cetera, et cetera. Not to say you can't learn anything. Photoionization models are fantastic. They're really great for intuition, but, Michaela clearly outlined why we need to couple these to galaxy formation simulations, and that's what we've been doing for years and years and years. And this is just an example from the Sphinx simulation, where we've taken a few thousand galaxies and we've fully post-processed them through dust radiative transfer, H2 region modeling, et cetera, et cetera. It took longer to do this than to run the simulation in the first place, which tells you how tedious it is. But you do get really cool images, and what's really nice is we have now a catalog that you can go download. It's 14,000 public images and spectra of almost any observable you could ever want. Here's just an example of one galaxy. We observe it down multiple different lines of sight. You can see by these, different blue dust attenuated spectra. So you can see how your SET fitting compares for line of sight observations. But, as I mentioned, this requires some sort of post-processing, which requires a huge number of assumptions. And so I can change those assumptions and realistically get something fundamentally different, which I think is a problem for predictions. And so for that reason, what I tried to do is develop a new code where we can just not do post-processing and not spend a year of my time working on simulations after I've already ran them. So the idea was that I want to take all of the physics that's in these photoionization models that allows us to model these H2 regions at very high accuracy, and I want to sort of shove that into a 3D galaxy formation code where we can get all this galaxy formation physics, for free. And then, of course, we want to connect everything to multi-frequency radiative transfer, do it in non-equilibrium, et cetera, et cetera. Okay, and you need to calibrate this. So we calibrate this in 2 ways. So first, we look at neutral gas. This is a very, very classic experiment that sort of Mark Wolfire and people pioneered in the 90s and before, where you just look at the temperature versus density curves for various different metallicities. The Milky Way's ISM follows sort of roughly this red curve, and our green line, is calibrated to match that. And you can see how the ISM cooling instability changes as you go to lower and lower metallicity. Okay, and so we calibrate at Milky Way metallicity, and then we sort of allow this to go to any metallicity that we want. Of course, this is neutral gas. What we also care about is ionized gas. So we just did some simple experiments where we take R code, Ramsey's RTZ, and we just set up a bunch of Stromgen spheres. So these are, your cloudy models or photoionization models. We just vary the gas density. We did this over metallicity, and you can just compare the emission line luminosities. And in fact, Ramsey's RTZ agrees better with cloudy than mapping. So these two codes will give almost identical results under the same settings, okay? So to just put this into perspective, this is my favorite AI image generation. The photoionization models are the spherical cows of H2 region modeling. And then Ramsey's RTZ it's still cow-like. I mean, we have subgrid modeling, but it looks, it's better, right? It's much more expensive, so we can't do this for every galaxy, but it's a slightly better approach, which I think it's very complementary, okay, these two. Let me give you 3 reasons about why it makes sense to do this. The first one, this is the dumbest thing you can do. You can take a Stromgen sphere and just add turbulence and put a star right at the center. And you can ask, how do the emission lines change when all we do is stir up the medium? And so this is our stirred up medium. There's a star right at the center. You see this, beautiful structure. Instead of a spherical H2 region, you get a butterfly structure. And then what we've done is we've just taken our favorite strong line diagnostics, O3 over H beta, N2 over H alpha, O32, as a function of various metallicities. The black stars are what you would get, running cloudy. And the cyan points with error bars are the mean and distribution over 10 realizations of just stirring that same box. And what you see is very strong systematic effects. Your O3 over H beta goes down, your N2 over H alpha goes up, and your O32 goes down. Okay? This is doing nothing but adding structure to the gas. So this is one of the main reasons why we need to do this. The second one is non-equilibrium effects often matter in the circumgalactic medium, which I know we haven't really discussed much of, but they also sometimes matter in the interstellar medium. So this is some work by Martin Ray where we've sort of added resolution elements where the gas is thermally unstable, which is where these effects arise, and you can see how the structure of the gas is quite different. This is an example of temperature versus density. Green regions are where you have too many electrons compared to equilibrium. Purple regions are where you have too few electrons. So what you see is that in sort of this dense gas over here, which is emitting in our emission lines, we have an overabundance of electrons, which is caused by the cooling time being much shorter than the recombination timescale. Whereas here, it's the opposite effect. It's where you have over-ionization, okay? You have a hotter gas for fewer electrons, and this is actually caused by cosmic rays heating the gas faster than it can ionize it. The other final point that I think really matters is that the distribution function of H2 region properties is going to bias our measurements of certain things, okay? So to give you an example, if you take a cloud that's completely isothermal and measure its metallicity using our favorite strong line diagnostic, 4363 over 5007, you get a perfect metallicity, okay? If you take that same cloud and just add temperature fluctuations, it depends a little bit on how you add them. But what you find is that your metallicity is always systematically low compared to the true value. And we fully understand the physics of this. The question is how bad is it? This is just a simple simulation. You don't have to believe the simulation, okay? This is just representative of what a possible realistic distribution function of H2 region properties could be. This is the one-to-one relation, and this is our best estimate using the gold standard method, and you find that it's systematically low by around 0.3 to up to 0.5 dex. So it is important that we take this into account. Okay, so what we're doing now is, one of the reasons I've been working on observations for the last 2 years is because this simulation has taken 2 years to run. We've plugged all of the physics I know into a single simulation called Megatron. It's an early forming Milky Way mass galaxy. It's got very high resolution, up to 1 parsec spatial resolution. Stars are individually sampled. It's got, feedback calibrated at redshift 0. 82 species, non-equilibrium chemistry coupled to, multi-frequency radiative transfer. There's various runs with different physics, but I'm going to start showing you some movies. This is sort of the time period just prior to a major merger at around redshift 4. You see your dark matter, your gas, your stars, gas temperature, and then my 2 favorite ones, your Lyman-Warner radiation, and then your ionizing flux. You see the ionizing flux is pulsating as the star formation rate is going up and down and up and down in this galaxy, okay? And any radiation transfer simulation could give you a movie like this. But what's really fantastic about Megatron is because we're solving for all this non-equilibrium chemistry coupled to the radiation hydrodynamics, The observables, including the emission lines, H alpha, O3, 4363, O2, N2, helium-2, this is now predicted directly on the fly from the simulation. The same pulsations that you were seeing in the ionizing flux, you can see them in the O3 map, okay? You can see the CGM around this galaxy is fluorescing in emission, which I think is quite cool. And since I'm quite short on time, I'm gonna cut this movie short and show you a few early results from the Megatron simulations, okay? So the first result is that the ISM holds really enormous potential for constraining galaxy formation models. There's actually 6 simulations here, only 4 are shown in this plot, where you're just looking at the stellar mass formed as a function of time, and basically no matter what we do to the star formation algorithm, okay, just changing the star formation algorithm, we always produce the same stellar mass by redshift 6 and then the same rough UV luminosity function, okay? But if you look into the ISM structure is completely different, and the distribution function of O32, which is something we've heard we can observe at high redshift, is completely different. So things like the UV luminosity function tell us nothing about this physics, but the ISM clearly does. And I think that's really quite a useful thing moving forward. These simulations have POP3 star formation. One of the things we're learning about POP3 is that it's a really short period of time. In fact, the first POP3 stars form, about redshift 27, and immediately afterwards, population 2 star formation completely dominates over population 3. So you can see for different models, the population 2 star formation rate, will change, but it's always dominant over population 3. That being said, the population 3 star formation rate is still extended down to low redshifts, which was perhaps a little bit surprising, because this is, a Milky Way mass galaxy. Another interesting thing is, population 3 stars and POP2 stars at these high redshift form at very high densities, okay? And this is direct observational implications. If you look at the UV slope beta of a population 3 star here at around 100,000 Kelvin, at these densities, you expect the beta slopes to be somewhere between -2 and -1. So if you're out looking for population 3 stars, do not look for blue galaxies, look for red galaxies. In fact, if you're making a cut at -2, you've just cut out every single one of your population 3 stars. So I think that's a really important thing moving forward. Another cool thing is that meta-line emitters start appearing very early in cosmic time, okay? So here's an early movie of Megatron. This yellow represents oxygen 3, so you can see that the metals are being enriched in the gas by these first population 3 stars. Ionizing radiation is breaking out of galaxies. That's why you're seeing the CGM and IGM illuminate in H-beta emission. But this starts to appear at around redshift 20 or earlier. So we still got a long way to go before we really get to that sort of pristine gas. That's a little bit tough for Webb, but I still think it's exciting to look at these early oxygen 3 emitters, because if you can get the other elements, we can start learning about population 3 star formation just purely based on yields. Switching away from gas phase to stellar metallicity, one of the things that I was a bit surprised by, this is iron to hydrogen versus carbon over iron. Some of the trends we see at redshift 0 in terms of, different metals are already in place by redshift 10 or so. So that was surprising to me how early these can in place by. And then this is sort of my last point. We have runs with, variable IMFs. This is an IMF that's based on gas density and metallicity from this, we just pulled it right out of this paper and shoved it in to see what happens. And what we find is that, the average brightening from these sort of IMF variations that's, empirically based on low redshift data gives us about 1.5 magnitudes of brightening, which could, of course, help us with this sort of overbright galaxy problem at high redshift. So my only conclusion is that, I think Alice and Dan really sort of highlighted how much we're in this sort of transformational stage in terms of high redshift ISM studies, purely just based on the spectra. And, me, Michaela, and many others are really trying to carry that momentum into the theoretical side as well. All this data from Megatron, my aim is to make it public by next summer. We're a team of 3, so if you're interested in the data early, please feel free to reach out. So thank you.
Thank you for a beautiful talk. We have lots of, okay, so let's start from Sunyeon.
Thank you for the talk. So can I ask, so how the, so in your calculation, maybe so you may resolve so code phase of the ISM, and so how the metallicity changes, so distribution of the code phase, for example, the mass distribution or so compactness of the cloud. So do you find any difference?
Compared to?
Maybe so different metallicity changes, so different cooling efficiency.
Yeah, you can see it, you can see it just from the 1D tests, right? So if you look at the temperature density curve at different metallicities, you see that, as you go to lower metallicity, first the cooling instability happens at lower densities, and then as you go to very low metallicities, you actually remove the multi-phase nature. And so this, in fact, is basically, this equilibrium curve shows up in the simulations as well, but then because, we have gravitational compression and we have turbulence and all that things, what ends up happening is that most of the gas is following this curve, and then you populate the region up here.
This also depends on the dust-to-gas ratio.
Yeah. So this feature is highly dependent. The sort of shift left then shift right depends entirely on your dust-to-gas mass ratio. That's exactly right.
Maybe the question is due to that difference, so the mass distribution, maybe the clump distribution of the cold phase. So are there any difference?
No, I mean, in our ISM, we're always dominated by the warm phase, even at solar metallicity. I mean, this is Kim and Ostreicher pointed this out, Mark Wolfeyer's pointed this out, so it's almost always warm phase dominated.
Yeah, thank you for nice talk. I have a little bit technical question. So you saw the non-equilibrium chemistry.
Yeah.
So what's the most important element? You mean electron, which is away from the equilibrium state? Which chemical species is the most important?
Oh, I mean, the electrons are almost always the most important because it depends on for what, right? I mean, for cooling, your electrons really matter, right? But then also oxygen-3 and carbon-2 are the main coolants here. But once you get to these very, very high densities in the neutral phase, you're mostly in equilibrium. Sure. But the non-equilibrium effects more so impact the ionized gas, which is where the emission lines come from. So it's the electrons that are controlling it, right?
So do you solve the non-equilibrium chemistry? Non-equilibrium level of transition, or only chemical species?
No, just the chemical species for now. Yeah, that's too expensive, unfortunately.
Okay, so Mark and then Alice.
Thanks, Harley, for a great talk, Mark Dickinson. I blinked and I missed it. About the population 3 stars and looking at red galaxies.
Yeah.
Say that again?
Yeah. so basically, if you, let's go to the plot. Oops, there it is. So if you look at UV beta slope as a function of effective stellar temperature, we think population 3 stars have a temperature of around 100,000 Kelvin. I mean, that's not me, that's Daniel Scher, right? So we can debate this a little bit, but they're probably pretty hot, right? And when you go to such high stellar temperatures, your ionizing photon production efficiency goes way up, so you produce way more nebular continuum, and that nebular continuum makes your galaxy much redder. So that gets you to -2. The thing though is that when you go to very high densities, you actually go above the critical density for 2 photon emission, which is keeping the spectrum blue. And so once you get above 10 to the 5, sort of above 10 to the 3, you see the curve for 10 to the 4 and 10 to the 5 goes up, you can get a beta slope close to -1.
Ah, because the 2 photon is suppressed?
You're suppressing the 2 photon and all you have left is free bound.
Got it.
So really we should be looking redder than about -2.1, I think is a...
But isn't this also dependent a bit on the escape fraction of the ionizing radiation?
Yeah, but I mean, we basically don't find that the escape fractions are very high. I mean, because at least in the simulations, we need those supernova to go off to really clear out the ISM. This is the one regime where Lyman alpha radiation pressure can work and sort of push you out, but as soon as the medium becomes turbulent, it basically doesn't do anything. And so for the low escape fraction objects, which is what we think most of them are, it's going to be red.
Right. Alice, you had a comment, maybe? Very quick one.
Thanks. No, this is wonderful. And I think we in Aurora would love to be in contact with you about various things. But I have a question about I think it was the Megatron part of your talk where you said that the 0.32 ratio is really sensitive to your different prescriptions. So what is it? What is that? I mean, that's like an ionization parameter.
Yes.
Probe. There was a different plot. It was like where you had the distribution function of 0.32. Not this thing, like later on when you had the simulation results. This thing here, you said.
Oh, yeah.
Yeah, so what is it reflecting?
Yeah, there's 2 things that are going on here. So you're right. So one, the ionization parameter is changing between these models. So the models that have like the 100% efficiency and they form all of it super quickly in really dense gas, those end up having higher ionization parameters, which is shifting you to higher 0.32. So you can see that. You can see this purple curve compared to this sort of like yellow curve. This is where we sort of force all the stars to form much more rapidly, and that's where this effect is coming up. But the second effect is actually one that I didn't appreciate, which was when we force the gas to get really dense before stars, you go above the critical density of one of the O2 lines. So you drop it by a factor of 2, and therefore O32 goes up just because of that.
Okay.
Yeah.
Thank you. I think that we need to stop here. So let's thank Harley again. And I ask